Hello and welcome back. So, this lecture we're going to get into numerical analysis properly. So thus far, we've been doing a lot of just toy examples. The first lecture we looked at just a bunch of examples throughout history. So we looked at what Archimedes did to approximate pi. We looked at Fermat's quadrature. We looked at some methods for calculating tables of logarithms. And but we didn't really go into any real depth there for any of those problems or other ways that we can use those same techniques. And then the next two lectures were all about defining what a metric is, because we need to be, if we're going to show that the things that we're going to be doing actually estimate the quantities that we're looking for, which is the whole idea of numerical analysis, we need to define what it means to be close. And so there's really only two metrics that we're going to be using. And so we didn't really go into too much depth as far as metric spaces, but I did want to define what the metrics were. So we have the Euclidean metric, which is on Rn. So it's basically where you get out of Pythagorean theorem. And we also have the sup norm metric, or the uniform metric, on space of continuous functions over a closed interval, which basically just talks about how you can talk about closeness of different functions. And more or less it boils down to being able to fit a window or envelope around one function to contain another one. And if you could do that, then that width of that envelope, or the smallest width that you can choose, ends up being the distance between two continuous functions. So in that light, I would like to move on and talk to you about some function approximation. And so this is actually going to use what we call the uniform metric, and demonstrating that these methods are actually going to start converging. And the best place to start, and this is a place that I feel should be familiar to everybody, is polynomial approximation. That's mostly what we're going to talk about as far as approximation theory goes. I think I'll throw in some stuff using kernel functions, because that's my own personal specialty, a little bit later on. And that's actually a bit of a more modern take on interpolation. There's also spline interpolation, which is pretty important. And so spline and kernel RBF interpolations sort of sit equal in a lot of contexts. But right now, we're just talking about polynomial approximation, and there's three main ways I want to go about talking about it. So the way that's probably the most familiar to most of you, and we've already been using it in all of our other discussions, is that of Taylor series. So a lot of functions can be represented by their Taylor series, or at least can be represented to some accuracy by a Taylor polynomial. This is something you learned out of calculus too. So we have looked at, say, the geometric series in the past, the series for the exponential, sine and cosine, etc. It turns out it doesn't always work out, and we'll talk about an example there. The function that causes trouble for us is like e to the -1 over x squared, defined over, say, -1 to 1, and you put that function is 0 at the origin, and we'll show that actually doesn't work out very well when you try to approximate it by its Taylor series centered at the origin. But for a lot of functions it does work out, and it works out really well for the exponential function, and sine and cosine. It actually converges fairly quickly. So what we're going to do today is we're going to go back and we're going to define what a Taylor series is, and Taylor polynomials. And then from there, we're going to look at a few examples, and then also get a formula for what we call the Lagrange remainder. Define the Lagrange remainder, which will allow us to demonstrate the convergence in the uniform metric later. We have to use a little bit of calculus, and this is where a bit of Calc 3 comes in. So what we're going to do is we're going to try to rewrite multiple integrals as a single integral. And the way you do that is what I mean by that is that if you take a look at, say, successive antiderivatives of a function, which you can each represent each one by yet another integral, it turns out you can write that entire expression as just a single integral times some special function. And that special function you get comes from when you exchange variables. So we're going to go through and we're going to prove that, and that formula of just one integral is called the Cauchy formula, the Cauchy integral for iterated integrals. Cauchy formula for iterated integrals, and not to be confused with Cauchy's integral formula, which comes from complex analysis. So we're going to go ahead and prove that integral formula, and then using that we'll be able to come up with a remainder formula for our Taylor series, and then subsequently we'll be able to get some convergence results in the uniform norm for, say, the exponential function and sine and cosine, etc. And some of that will be left up for homework, just for you to get some exercise, get some example, get some some of it will be homework just for you to get some practice. In any case, we can go ahead and get started, and I'll stop my rambling. I think I should have had more coffee this morning. Okay.
Okay, so let's go ahead and get started. So today what we're going to be talking about is really Taylor series and polynomial approximations. And Taylor series. So generally speaking, where we have the goal of polynomial approximation is given a function f from, say, over some interval, say a to b to r, that is, say, continuous, can't spell, differentiable, etc. We might need just continuous, we might need it to be continuously differentiable, we might need it to be infinitely differentiable, etc. So given this function, find a polynomial p of x such, sorry, I should say, rather, be more precise, differential and an error epsilon greater than 0, find a polynomial p such that, say, the distance between f and p is less than epsilon. What that means is that we want the maximum of x over, say, a b between f of x and p of x to be less than epsilon. So more generally, we have some sort of function f, put it in red, and we have some sort of epsilon. So here, let's make it a little bit bigger. So here, so that would be epsilon. If we fit a window of width epsilon around our function, then the idea is that we want to be able to find a polynomial, let's put it in pink, that sort of stays within this window over, say, going from, say, let's call this A, and let's call this B. And so that's the general idea. And so we're going to look at a variety of methods that do this, and the first method comes straight out of Calculus 2, and that is that of Taylor polynomials. So what we're going to do is let's go ahead and let's figure out how you could find out this approximation from the beginning. So we're going to assume that f is n times differentiable, and let's say in the neighborhood of a point A in the reals. Okay. So what can we say? Let's just say, and we'll just say that neighborhood is A minus delta to A plus delta for some delta bigger than 0. Delta could be big, could be small. It's just, this is the interval that we're talking about. Okay, so now let's suppose that x is in this interval, and we'll call this interval I. Then what we can do is we can write f of x should be able to be written as f of a plus the integral from a to x of f prime of t, let's say t1, dt1. We're going to have to keep doing this. Okay, so we can think of our first approximation or our 0th approximation. So over here on the right, we'll keep track of this. So our first approximation, if we neglect the integral, would be that would be t naught of x is equal to just f of a, or the constant function. Okay, now let's do this again. For each one of these guys, t1 is actually in the interval, just like x was. So then we can write f of x is equal to f of a plus now the integral from a to x of f prime at a plus the integral from a to t1 of f prime of t2 dt2 dt1. Okay, now actually, since this is constant, we can go ahead and integrate that. That's no problem. So that gives us that f of x is equal to f of a plus f prime at a times x minus a plus the integral from a to t1 of f prime of t2 dt2 dt1. Yeah, and so this should have been all around there, and we're missing the outer integral a to x. There we go. Okay, so we distributed this integral through to both of these guys. We can integrate just this piece, and then this one becomes a double integral. Okay, now if we take a look at this, it tells us that our first Taylor approximation is going to be f of a plus f prime of a times x minus a. Okay, not bad. Okay, so next, what do we see? We're just trying to come up with a general formula. You should know it already, but you know, just for practice. Next, we have f of x is equal to f of a plus f prime of a times x minus a, plus now we have two integrals, both going from a and one going to t1 and one going to x. But now I can write this again as using fundamental theorem of calculus. We get f prime, oops, that should have been f double prime. Oh man, sorry about that. So we get f double prime plus the integral from a to t2 now of f triple prime of t3 dt3 dt2 dt1. Okay, so now in order to compute this quantity, well, we're going to have, so again, we have this integral applied to both of these guys. And now if we want to compute this first one, we're going to have to do a double integral. So let's go ahead and do that, and clear up some space here on the right so we can play with it. So this is going to give us, say, f of a, again, plus f prime of a times x minus a, plus the integral from a to x of f double prime at a of t1 minus a times dt1. Is that t1? dt2, sorry. No, that's right. Okay, sorry. dt1 plus now the integral from a to x, the integral from a to t1, and the integral from a to t2 of f triple prime of t cubed dt3 dt2 dt1. All right. Okay. So this one now actually has some dependence on t1. So we actually, if we're going to integrate it, we need to integrate it like a polynomial. So t minus a, t1 minus a integrates, and let's see what we get. So we're going to get f of a plus f prime of a times x minus a plus now we're going to get f double prime of a, that just pulls out. And so the integral now is going to be t1 minus a quantity squared divided by 2 evaluated at a and x. Okay, plus all this stuff, which is going to take it to on the right, so I'll just copy it. There we go. And oops, one small edit. There. Okay, cool. And so finally, this quantity here, we can get at it, and that is going to be equal to f of a plus f prime of a x minus a plus f double prime of a divided by 2, and what we're left with is x minus a squared plus now this triple integral a x t1 t2 f triple prime t3 dt3 dt2 dt1, right? And so this quantity here ends up being a capital T2 of x. All right, so that gives you an idea how to find these Taylor polynomials, and more generally, what we're going to find is that Tn of x is equal to f at a plus f prime at a times x minus a plus f double prime of a times x minus a squared divided by 2 factorial plus all the way down to f nth derivative at x minus a to the n divided by n factorial. And since honestly though we have to keep iterating all this, if we're only saying it as n times differentiable, then we could really only take this to a certain point. So we'll just stop at t n minus 1. Say divided by n minus 1 factorial times x minus a to the n minus 1 divide and yeah, maybe just move this over. There you go. So that's going to be n minus first Taylor derivative, and so the nth derivative is ultimately going to end up being used in the remainder formula. So so basically what we find then is that f of x minus t n minus 1 of x is equal to a whole bunch of integrals, f to n of, say, t, let's see if I get the indexing right. Yeah, so it's going to be a tn. Then we're going to have dtn all the way up to dt1. And all of these points are going to be from a to somewhere. And it's going to be a to tn minus 1 up to a to t1, and it's going to be up to x, right? And so this is our formula, and this is what we're going to be trying to get a hold of as far as its size, in order to demonstrate that we actually end up getting convergence sometimes. So now, so we call tk of x the kth Taylor polynomial of f centered at a in the real numbers. Okay, so so now that is how you derive Taylor polynomials and Taylor series. Although I should tell you what a Taylor series is. For an infinitely differentiable function, the corresponding Taylor series is given as, so I'll just call this t of x is equal to the sum of n equals 0 to infinity of f of n, the nth derivative at x, divided by n factorial times x minus a to the nth power, right? And so this should all be rather familiar to you. Okay, so we can go ahead and do a few quick examples, just to remind you how all this works. So let's take a look at the easiest example, and that easiest example is the exponential function. So, right, and so we'll do it centered at a. So we'll say, given f of x equal e to the x, find the Taylor series for f centered at a in the real numbers, right? So what is that going to require us? Well, we need to compute f of a, we need to compute f prime of a, we need to compute f double prime of a, etc. But that's not too hard. We know that in each case the derivative e to the x is just e to the x, so it's going to be e to the a equals e to the a equals e to the a all the way down. So so t of x then is going to be the sum n equals 0 to infinity of e to the a divided by n factorial times the sum times x minus a to the nth power. Okay. And something that's interesting about that, just for fun, you can see that then you can factor out e to the a, and you get sum n equals 0 to infinity of x minus a to the n over n factorial, and this can be seen as just plugging in x minus a into e to the x. So it's going to give you e to the a times e to the x minus a. So from the Taylor series, we can actually demonstrate that you have this product property of exponentials. Okay, so yeah, and so this should, we haven't proved it yet, actually be equal to e to the x, because this is the Taylor series of e to the x. So But yeah, we'll have to prove that later. Okay, so let's come up with the next Taylor series. And I might as well do it for the next one. So given f of x is equal to, say, cosine of x, find its Taylor series centered at the origin. And these are what we call a Maclaurin series, right? So Taylor series centered at 0 is a Maclaurin series. Okay, so let's go ahead and do it. So here we go. We have, we know what f of x is cosine of x. We know f prime of x, and that is equal to minus sine of x. We know f double prime of x is equal to minus cosine of x. And let's do a couple more. F triple prime of x is equal to plus sine of x. F, the fourth derivative at x is equal to cosine of x. Okay, now at 0, so f of 0 is going to give us 1. F prime of 0 is equal to 0. F double prime of 0 is equal to -1. And f triple prime at 0 is equal to 0. And f quadruple prime of 0 is equal to 1. And after that, everything just keeps repeating. So when we write the Taylor series here, we might as well just skip over all the odd ones. So we're going to write n equals 0 to infinity. But here we're going to write x to the 2n. We're going to have, take a look at only the 2nth derivatives. So at 0 divided by, say, 2n factorial, because all the odd ones disappeared. Then we have x minus 0 to 2n. And putting that all together, we get n equals 0 to infinity of -1 to the n over 2n factorial x to the 2n. Okay. So this shouldn't be any big mystery to you. Hopefully everybody is fairly bored with me going over these two really simple examples. This comes straight out of Calculus 2, and so you should be familiar with it. But what we haven't done yet is we have not proven that the Taylor series converges for either of these cases. And so that is something we're going to have to end up doing. So we would like to ultimately get a hold of a size on this guy. And in order to do that, we need to use Cauchy's integral formula to turn this from like a crazy multiple integral to something that is maybe more manageable. So let's go ahead and do that. And so what we're going to be talking about now is called the Cauchy formula for iterated integrals. So what I'm going to do is I'm going to write f to the minus n of x is equal to, say, the integral from a to x, the integral from, say, a to t1, all the way down to the integral from a to t n. And, or rather, let's say tn minus 1. And so it's going to be f of tn, and then we're going to do dtn all the way up to dt1. Now it turns out that this is equal to 1 over n minus 1 factorial times the integral from a to x of x minus t to the n minus first power times f of t dt. Okay. And so, of course, this doesn't work for just any function. We'll assume that that f is continuous over, say, a, b, and x and a both live in AB. Okay, So if that happens, then we say that then the following holds, and we have this. So we'll say if f is continuous over ab and x and a are in ab, then ta-da, formula. Okay, so how do we get at this? So we're going to go ahead and prove this by induction. So proof by induction. So we're going to start with f of -1 of x, and we know that this is just going to be written as integral from a to x of f t dt, or ft1 dt1 if you like. But this is the same as saying 1 over 0 factorial times the integral from a to x of x minus t to the 0th power f of t dt. 0 factorial is equal to 1 by convention, and so there, the base case is established. So now we will assume that the formula holds for n minus 1. So now if we take a look at f of minus n of x, this is integral from a to x, so integral from a to t1, all the way down to integral from a to tn minus 1, f of tn dtn, all the way down to dt1. Okay, now if we take a look at this inner portion here, let's move t1 over here, and we'll include dt2. If we stop right before we get down to t1, and we get down to this is the n minus first antiderivative. Let's figure out a nice way of writing that. So it's f of minus n minus 1 of t1. Okay, so by the induction assumption, what do we have? Well, this is going to give us, say, the integral from a to x. The exterior doesn't change, so it's going to be still an integral on t1. But on the inside, we're going to have 1 over n minus 2 factorial, and we're going to have the integral from a to t1 of t1 minus t to the n minus 2nd power of f of t dt. Okay, so now what we need to do in order to complete this is that we need to exchange the integrals. Really, in this kind of analysis, that is really the only thing you can do, and so we're going to go ahead and try to give that a shot. Okay, so we're going to go ahead and do an exchange of integrals. And so what we're going to do is we're going to take a look at these axes. We're going from, say, we're going to be thinking of this, I'm just marking this like a 0, but this is really starting at a. And this one is going to be, say, the axis t1, and here we're going to have t. Okay. And so, basically for any fixed t1, we are integrating from a up to t1. And this line here is where we have t equals t1. And so t ranges from a to t1, so a to t1, over and over again. Okay, all the way up until t1 stops at x. Okay, so now we want to exchange these variables. And so we're going to say now for fixed t, what is t1 doing? Well, in this case, for fixed t, t1 should be going from t all the way up to x. So this is t1 doing this. And so if we go ahead and exchange the integrals, we're going to have 1 over n minus 2 factorial. And we're going to do the integral. So a t is going to be ranging from a to x. But now we have t1 going from t to a. T to x. And then this on the inside is we're going to have t1 minus t to the n minus 2, that hasn't changed, and f of t, and then we have dt1, dt2. Or sorry, not dt2, but dt. Okay, so now we can go ahead and integrate. So first of all, we notice that f of t can be pulled straight out of here. It has nothing to do with t1, so we're going to do that. This is going to give us 1 over n minus 2 factorial times the integral from a to x of f of t, and now we're going to have the inside integral from t to x of t1 minus t to the n minus second, and we have dt1 dt, right? So now we get 1 over n minus 2 factorial and integral from a to x of f of t. And then if you work out that integral, that is going to give us x minus t divided by n minus 1. And this is dt. And so then that gives us our formula, 1 over n minus 1 factorial, integral from a to x, f of t, that should have n minus 1, to x minus t to the n minus first power dt, right? And there we go. That's our formula. Okay, so that is a Cauchy formula for iterated integrals. So now we can go ahead and apply it to this formula here. So we see we have this, but then this now can be written like this. We have 1 over n minus 1 factorial times the integral from a to x of f, the nth derivative, at t times x minus t to the n minus 1 power dt. And let me just make sure I did that right. And variables. Yep, and there we go. Okay, so that gives us a formula that we can get at, and this is what is going to be the remainder after we subtract off the n minus first Taylor polynomial. So let's go ahead and extract some sort of bound on this. So overall, we care about the difference here, tn minus x, f between f of x and tn minus x. So we'll just call this theorem. We'll put error bound on this theorem. Okay, so so this quantity is less than or equal to m over n minus 1 factorial times x minus t to the x minus a to the n divided by n, I think. Does that work out? Yeah, so that should work out. So ultimately, it should be divided by, say, n factorial. All right, so proof of that is pretty easy, and we should also say where m is equal to the maximum value of the absolute value of the derivative of f at x for x in the interval that we care about. So we'll just call this the interval AB. Okay, so proof. Really straightforward after everything we've done. Basically, if f is n times continuously differentiable, since fn of x is assumed to be differentiable over AB, the extreme value theorem guarantees the existence it guarantees the existence of the bound. Bound M. Okay, so as, let's say, M equals the max of x in AB for the absolute value of fn of x here. Okay, thus we have as the value of f of x minus t n minus 1 of x is less than or equal to the 1 over n minus 1 factorial of the integral from a to x, moving the absolute values on the inside. It makes it larger, so we have this, and then x minus t to the n minus 1 dt. Since x is sort of on the upper end of the interval here, t is never going to get bigger than x, so this is always positive. So I can just leave that. Okay, so this is less than or equal to 1 over n minus 1 factorial. I replace the absolute value by m to make it bigger, and so we can pull that out. And then we have the integral from a to x of x minus t to the n minus first derivative dt, and then taking that integral, what we're going to find is going to be 1 over n minus 1 factorial times m, and we're left with minus x minus t to the n divided by n, evaluated at a and x. And so ultimately that gives us 1 over n minus 1 factorial times m times x minus a to the nth power over n, and we can finally conclude with our formula. Okay, cool. And so this is a bound on the remainder formula. And so stop there. Okay. So now let's take a look and see how we can use this formula to demonstrate that we get convergence of our Taylor series. So what we have is that we're going to assume that f is n times continuously n times differentiable with fn of x continuous over AB, and then it follows that f of x minus t n minus 1 of x is less than or equal to the maximum or the absolute value of fn of x for x in, say, AB, times the absolute value of x minus a to the nth power divided by n factorial, where t n minus 1 is the n minus first derivative, Taylor polynomial centered at a inside of AB. And so basically we should say it follows that for all x in AB. All right, there we go. So since f, and so basically this gives us a bound for all x, and in that interval, and so what we can say is that the uniform distance, so we'll say the supremum, or say the maximum, for x in AB of f of x minus tn minus 1 of x is less than or equal to this quantity here. Copy, paste. But then again, since x and a are both assumed to be inside of AB, we can just write b minus a, or length of the interval. Okay, so that gives us a uniform bound that's independent of x and independent of a. And so we see that as, so generally speaking, as n goes to infinity, this quantity goes to 0 as long as the derivatives don't grow too fast. Okay, so what do we get then? So here we're going to have a proof that e to the x is equal to the sum n equals 0 to infinity of x to the n over n factorial. All right, well, we know that e sub x minus, say, t n minus 1 of x then is less than or equal to, and let's just say over, say, negative a to a. And then we can take a to infinity later. But basically, for Taylor series centered at 0, or the Maclaurin series here, we get this. So we're going to have the maximum for x in, say, minus a to a, and of f, the nth derivative at x, times a minus a is going to be 2a to the nth power divided by n factorial. Okay, so what we can see is that this term is always going to go to 0 because a to the n and 2 times a to the n is going to be outstripped by n factorial pretty quickly. And we'll also note that fn of x is equal to e to the x, and thus is bounded, or is identically, bounded by e to the a over minus a to a, right? And so that's a fixed constant. So therefore, we have e to the x minus t n minus 1 x is less than or equal to e to the a times 2a to the n over n factorial, and this goes to 0. Thus, the Taylor series converges to e to the x. All right, so good. All right, so now we're going to talk about an example where it doesn't work. Okay, so now we've seen that the Taylor series actually converges to the exponential function, but why don't we take a look at a function where the Taylor series isn't going to work out for us? And so this is another example, maybe a counterexample of the Taylor series formula converging. So here we have, say, f of x is equal to e to the minus 1 over x squared and 0, and this is for x not equal to 0, and this is for x equal to 0. So if you think about it for a second, basically, this, first of all, it's an even function, and if we aren't at 0, it's roughly a Gaussian, kind of. As x goes to infinity, we're going to have e going to 1, e to the minus 1 over x squared going to 1. And then as x goes to 0, negative 1 over x is going to have a negative asymptote to infinity, which is going to pull the exponential down here. And so again, like I said, even function. And then basically, we have an undefined value at x equals 0, but we avoid that by defining this function separately by putting 0 right there. So what you can do then is you can take a look at the derivatives of this function. So let's say for x not equal to 0, we have f prime of x is equal to 2 over x cubed. The negative sign ends up canceling with minus 2 popping out there, times e to the minus 1 over x squared. And we can again take two derivatives, and then what we're going to have a product rule coming out here. So it's going to be minus 6 over x to the 4th. Then we're going to have times e to the minus x squared, but we can factor that later, plus 2 over x cubed, and then times e to the minus 1 over x squared, right? And so forth. So if x isn't 0, these are the sort of things we're going to get. And basically what we're going to see is that, as x goes to 0, we have f prime of x tends to 0 as well. And ditto for x double prime, etc. And basically, this can be left as an exercise if you'd like, where basically you can show that the limit as x goes to 0 of e to the minus 1 over x squared over x to the n is equal to 0 for all n. And that would basically take care of that. So we get a whole bunch of continuous functions if we take these functions and we define them all to be 0. So we're going to define fn at 0 to be equal to 0. Okay, so then that's what you get. So basically, we're going to end up having a whole bunch of reciprocals of powers of x and times this exponential here. So and this makes it makes each of these derivatives continuous. So this makes derivatives continuous, right? And you can verify that continuity by proving that exercise. Okay, so what do we get then? Well, if you take a look at the Taylor series, t of x, certainly this converges for all x to something, but it isn't going to converge to our function. So remember, the Taylor series is n equals 0 to infinity of f of n at 0 over n factorial times x to the n, or the Maclaurin series in this case. But this is all 0, because the nth derivative at 0 is 0, and so the entire Taylor series gives you the 0 function. but we know that f is not 0. So you can say, well, this was piecewise defined function. Well, that doesn't matter. Basically, we've shown that f is infinitely differentiable and continuous. And each derivative is continuous. But that follows from it being infinitely differentiable, so we can save it there. So typically we say that f is c infinity, where the power on c represents how many derivatives you can take, resulting in a continuous function. So, so that says that even if we have a really well-behaved function, a function that is differentiable everywhere and infinitely differentiable, in fact, we even have the Taylor series doesn't actually converge even for any x other than where we started at 0. So the only time this matches is when you look at f of 0, which is 0, and that's not really that meaningful. So, but yeah, that's the idea. And so this tells us that maybe Taylor series isn't always going to work out well for us. There are a few examples where it does, and we saw that, for instance, for the exponential function here. And it'll work out for sine and cosine, and so we can make that as an exercise as well. Show convergence for sine of x and cosine of x. But yeah, so yeah, in any case, so then this motivates us to look at other ways of approximating functions with polynomials, because it looks like this is going to end up not working out all the time. But there are some methods that do. Interpolation is going to be one that works out well, but not all the time either. But following that, we will look at another approach to polynomial approximation through Bernstein polynomials, and we'll talk about that later. All right, so we'll pop back to my office and wrap up the lecture.
Okay, so that was Taylor series. So this should have been largely a review of Taylor series for you. Almost everybody, or everybody really, should have seen it through Calculus 2. Maybe the new information is the Lagrange formula. Sometimes that was included in some Calculus 2 classes, but other times not. And then, of course, convergence and the uniform metric is new as well. But we need to be careful when we use Taylor series approximations. They come up a lot. Engineers use them to do things like expand a differential equation at a point, and they use, like, say, the first one or two terms of the Taylor series in order to get a quick estimate of what that function does locally for that differential equation. Often it's used to establish stability and things like that. But on the whole, as a function approximator, it generally operates rather poorly, or at least on a large scale. One big reason of that is that in order to make the Taylor polynomials, you need to take successive derivatives. So if you are just dealing with a collection of data, like a whole bunch of samples of a function, and you don't have access to that function itself, what ends up happening is that you need to take a lot of numerical derivatives. And you can't really rely on numerical derivatives past, say, the first numerical derivative, or maybe the second. But the third and fourth one are really nearly impossible to get out of a data set. So, yeah, that ends up being an issue. And even if you want to do it, if you have the function available to yourself, you need to compute a lot of derivatives. There is a bit of an industry in, say, computer science, and I've seen it also in mechanical engineering, where people develop algorithms for automatically taking derivatives. We can put together some quick slapdash formulas in MATLAB, and we'll do that later, to generate some coefficients for Taylor polynomials. It's a good exercise in using a symbolic toolbox, but it's slow, and it generally it's not really a good tool to use. And then, of course, we've seen a continuous function where the Taylor, a continuously differentiable or even an infinitely differentiable function, where the Taylor series doesn't converge at all. And so that ends up throwing a big red flag for the method. And we would like to be able to assume only continuity and still get good polynomial approximation. And so, so that's going to be a challenge that we're going to confront again when we talk about interpolation, but then also we will give you at least one method that will always converge to a function just from the function being continuous, and that'll come maybe like 2 or 3 lectures down the line. But yeah, so we're going to stop there, and thank you for listening.